Tuesday morning at 3:31. She's about an hour old here. So we adopted her. We've been in touch with the birth mom, and we got to be in the process the whole way. We got a couple more. Emma. So you can barely read it, but there's a little thing, Emma. And this is a good one. So I think I had a pretty good excuse for canceling office hours right before your test. Sorry that was the timing of it, but I hope you understand. Okay. So what's going to happen is for recitation today, you're going to have recitation. It won't be a quiz, but it will be a worksheet that you have to hand in at the end of class. You can work together on it, okay? Let's see. If the worksheet in class involves graphing calculator, make sure you bring your laptop. Because you're going to be using, I'm going to show you, you're going to be using graphing calculator on that worksheet. Okay? And then, at the end of recitation, you're going to get the homework for Monday. Okay? That's going to be a handout. The homework for Monday involves, not my math lab, but it involves the book. Okay? So, if you have the physical copy of the book, you can use that, but if you don't, if you just have the online access, I'll show you quickly how you can get to the book. Over here on the left, on the home page, it says Multimedia Library. Just click on that. Click Multimedia Textbook, and then Find Now. And then it comes up with links for every section. You're going to be in 3.2. When you click on the section, it uses this. In order to use the online multimedia stuff with the textbook, there's like 3 or 4 different plugins and software that you have to correct in your computer. So that was showing one of them. So you should get to this, and then you just click on, these are all the parts of the section. Now, if that doesn't work, you go back to the home page, and what you need to do is this thing right here. See, it says browser check. This browser check will help you figure out how you need to get the updated plugins or download some software online to make sure that you can run that multimedia stuff. Okay, most of you probably have the physical copy of the book. You can use that. But if you just have the online access, you're going to have to get that stuff online. Okay? In terms of the book, they use terminology that we have not really introduced. So I've posted on Blackboard this kind of translator. Okay? So if you come to something in the textbook or in the questions in the textbook, and just look in, and if you don't recognize it, it's not familiar, some kind of symbolism, then take a look over here on the left side and see if you can find it, and then over here on the right is the language we've been using for the same thing. Okay, so this is going to be helpful if you come across symbolism or notation in the text or in the text problems that you don't recognize. This is a kind of a translator for that. Okay, I'll show you where I posted that. That's posted in assignments. On Blackboard, you go to assignments. See Monday, October 22nd. There it is, text and terminology. So that's not the assignment, that's just this helpful translator thing. The actual assignment that we do Monday, the first worksheet you're handing in at the end of class in recitation. The second sheet you're doing over the weekend. So there's kind of a two-parter to this homework. Okay, the second part, which you're working over the weekend, is what involves the text. Any questions about those nuts and bolts? Okay, as far as exam 2, I just brought the Scantrons over to processing, and if everything is normal like it usually is, they'll get me the results back this afternoon. There's a chance they might not, and then we'll have to wait till Monday or Tuesday, but if they can get them back to me this afternoon, I can start work on that and post the results this weekend. Okay, any questions about nuts and bolts administration stuff? Okay, so the first part of the course, what did we work on? Accumulation to rate or rate to accumulation? The whole first part of the course. Rate to accumulation. And then in the last week, since just before the test, now we're working on turning the tables here, starting with the accumulation function, building the rate function from the accumulation. Okay, so if we have an accumulation function, how is it that we were able to build an exact form of an accumulation function? So this is an equation for the accumulation function, but what is it that we did that was an exact accumulation function? What is it that we did was an exact accumulation function? Everyone should know this. Will. Okay, so the integral of what? So be more specific. What integral is an exact accumulation function? Richard. Okay, integral from a to x of what? Integral a of x of what? F of x? 3x squared? 3t squared? What is this again? That's an accumulation function. So do we want the integral from a to x of 3t squared? Yeah. What do we want? Yeah, so it would be the integral from a to x of the rate function, right? The rate function. Rt dt. So that would be equal to, so 3x squared is equal, if 3x squared is an accumulation function, then it's equal to the integral from a to x of, what does Rt dt represent? Rt times dt. What is that? What does that give you? Yeah. A little bit of accumulation, right? And then we do what to those little bits? Add them up, right? So that long form AX equation, that was what that was about. Adding up all the little bits of R times delta X, R times delta X. Okay? So the question is, so we know this 3x squared is equal to some integral of a rate function dt. The question is, we don't know what that rate function is. So this is part two now. This is the other side of the story, right? The other side of the story. You have an accumulation function. What's the rate function? Okay, so here's an exact accumulation function. And so in class on Friday and in Dr. T's video, we laid this all out. So if we're starting with an exact accumulation function and our goal in the end is, what is our goal in the end? Exact rate function. What's the first step in that journey? We've got exact accumulation function. What will the first step be in general? He wants an approximate, what? An approximate accumulation function. Can you just describe what will that look like? What will the approximate accumulation function look like? Anybody here? Jim. Here's our exact accumulation function. What will an approximate accumulation function, what will that look like? Piecewise function, and how will it relate to this? Okay. Okay. Can it be down here, like in negative y territory? Around the same place, just somewhere in here? Yeah, so we're going to form that from, how are we going to form that approximate accumulation function? So where are those breakpoints going to come from? So, yeah, we're trying to replicate this. So we're going to pick off points. Every delta x, we're going to have points. And we're going to pick off those points, and then we're going to form this. So I'll just do a large delta x, we did this last Friday. And then we're going to approximate this accumulation function by doing what? The red is curved, but it's almost straight that you can't tell the difference. But so the blue is a piecewise linear function that's trying to mimic the exact accumulation function. Why? Why do we do that? Roman?
So once we have the approximate accumulation, we then approximate the rate change function.
Okay. And why does that help?
Then you can find the exact rate change from the approximate rate change.
But why does having that the way that I just drew that? Why does that help us get an approximate rate function?
You get a constant rate of change.
That's right. Yeah. So can you see the black is our approximate accumulation function? The reason we do it is it gives us constant rates. We know constant rates are easy to work with. Mathematically, piece of cake. So we can do all kinds of, or make those calculations quickly with constant rates. Okay? So our goal is to come up with, first, an approximate rate of change function from the approximate accumulation function. So here's any point x. How am I going to come up with, so if I plug x into our approximate rate function, I'm going to get the rate of change right there. What do I need to do that? What do I need to do? What do I need to calculate that rate of change? Somebody new? We'll go back. Okay, how am I going to get that? You tell me. How am I going to get, these are the slope of the line, which is the rate of change. How am I going to get that? What do I need to calculate that? What's that? Like the width of the interval? Oh, you need a point. You need a point here, and? Yeah, if I have the coordinates of those points, then I can calculate what? Line. Changing y, we're changing x, right? So we said that given a point x, the point on the left side of the interval is going to be left x, and then f of left x. Then the right side of the interval will be left x plus delta x, f of left x plus delta x. So what we did Friday, and Dr. T started out with that in the video. So then changing y, we're changing x, is our approximating rate function. Changing y over changing x. So suppose this x right here is 0.73. How will r of 0.73 compare to, say, r of 0.61? What do you think? Isabel? So this is this particular interval is from 0.6 to 0.8. So how will r of 0.73 compare to r of 0.61? She's saying it's going to be the same because they're in the same interval. Ashlyn, you agree? Okay? Yeah, because what is this rate? The output of this rate function is not the y value, not the accumulation, but it's the constant rate of change in that interval. It's the constant rate of change. So as long as we pick an x in that interval, it's going to spit us back to the left, which is here, and it's going to then it's going to give us the right over here by adding delta x to it. So the calculation will be exactly the same for 0.73 or 0.61. How will r of 0.73 compare to r of say 0.29? Nick?
Won't the rate at 0.73 be greater than 0.29?
He wants greater at 0.73 than at 0.29. Because the rate of change here is represented by that slope. The rate of change here, it's not growing as fast here. You see? So yeah, those will be different. Now how about 0.29 versus 0.38? Crystal. Same rate, okay? Because they're both those x values will give us that left to calculate the rate of change and that right to calculate the rate of change, and it will be that same constant rate. So therefore, what kind of function is Rx? If we were to graph Rx, what kind of function would we get then? What's that? Yeah, what will it look like? If we graph this approximating rate of change function, he wants a step function. Yeah, because in every interval we have the same constant rate of change. So if in the next, I don't have it here in this graphic, but if I were to graph now R of x, there would be some rate of change up to 0.2, and then suddenly that rate of change would be higher. And you get steps. You get steps. Okay, so then we're going to let delta x get small. So we're going to make these intervals smaller and smaller. And then let's let delta x be h. It's just a simpler terminology, just a little quicker. And then you saw in Dr. T's value that when that's true, when you let delta x get small, the starting value of a, where you start a, doesn't really matter because we're really focusing on rates. So what does Rx become then? When we do that, we get the exact rate function for very, very small values of h. And what used to be left x, when delta x is small, remember this used to be left x, beginning part of the interval. But if delta x is very, very small, think about a very, very small interval, then it's kind of like every x, right? Every x is the left side of the interval. And what was the idea of this? That as you let h get very microscopically small, that these are essentially the same value then. What was that idea from the video? Sam, remember? Limits. That's so, and so this idea of letting x get very, very, very small, we've been talking about limit all semester. Okay, so we can write it this way. So this is our exact rate of change function. What does the numerator represent? What's that? She wants change of y. Savannah, agree with that? Numerator. Change of y. Lauren, agree? Okay, and what does the denominator represent? Yeah, because it's rate, right? What is essentially rate is what? How do we calculate rate? Delta y. It's a rate function, so it's based on delta y over delta x. Okay? So this is our change in y, this is our change in x, and we have to, as we let h get very, very small, the step function, that step function of rates, then becomes a continuous rate function. Okay, so we got this accumulation function 3x squared. I'm going to show you in graphing calculator how this is pretty slick, how we can use this. Okay, so here is our, let me write it out again, our exact rate function. Okay, here's our exact rate function. And so notice that it took us about a month to make this journey from exact rate to exact accumulation. It took us less than 3 classes to make it back, right? Because we had all these building blocks in place. We understood all the parts. So going backwards now is much easier with all the groundwork that we laid. Okay, so here's our exact rate function. And so in order to get this rate function for a specific, say, accumulation here, 3x squared, we're going to assemble this for our particular change in y over change in x. Okay, so what does this function say? It says to take the input and square it and multiply by 3, right? So the question is, if we just want to look at what is f of x plus h? What's the input represented by f of x plus h? How about Kirsten? What's the input for f of x plus h? Okay. Dalton? Remember back when we talked about symbolic notation for functions? Will? No, so just looking at this, forget about that. Just the notation, f of x plus h. What is the input? X squared plus h. Will, you want to try again? So just looking at this, what is the input into the function? Okay, I think you're just making it too hard. Daniel, what were you going to say? H above x. Yeah, x plus h. That's the input. This is telling us to input the quantity x plus h into the function. So if this function says, take the input and square it and multiply by 3, and then if the input's x plus h, then what is f of x plus h? Saskia?
Would be 3x plus h quantity squared.
She wants 3x plus h quantity squared because the function says take 3 times what? The input squared. Okay, so what the function says, take the input, square it, multiply by 3. What's the input if you have f of x plus h? X plus h, so you take that and square it, multiply by 3. All right, what is, then, to get our change in y, we're going to take f of x plus h minus f of x. Katie, what's f of x?
X squared, 3x squared.
3x squared. So there's our change in y for this particular function. At any value x. Then we're going to divide it by h. Okay, watch this. It's pretty slick. So I'm going to keep copying and pasting so we can see all the steps. But what we need to do now is we need to expand this and see if we can get a simpler form of this expression. So I can highlight the 3x plus h squared. If you go to the math menu and you can hit expand, boom, does it for you. All right, so I'm going to copy that for the next line. Okay, so just we can visually see here what's going to happen now. We're going to keep simplifying this. What will happen in the numerator? Can you see? You see that we have a 3x squared and a negative 3x squared. Those will be 0. So we could do that ourselves, but simplify. Okay, and I'm going to copy next line. No, didn't work. Okay. What do you notice about the numerator now? Okay, they both have an h in it. So you can even have it factor for you. So if I want to pull out h, so I select h, grab it there with a little hand and pull it out. And now, why does that help us? What happened? Now I have h over h. What's h over h? 1. So, algebraically, this right here, our starting, it's called the difference quotient. It's like change in y over change in x. difference of y's over difference in x, the difference quotient. So we did all legal math steps there, and we got that that difference quotient is equal to this. So what is this? This is like an approximating rate function. This is an approximating rate function for a given delta x or a given h. All right, so how do we get the exact rate function? Connor.
You made delta x is h really small.
Yeah, so we're going to say let h get, h arrow 0 would mean let h get atomically small. Let h get atomically small, and then, so as that happens, 6 plus 3h becomes 6x. Okay, got our exact rate function. Okay, you will be doing this process. Hopefully at the end of class, I'll have time to let you try this on a different example. So I'm going to see if we can get there. But you'll be doing this for your homework, okay? And you're gonna do some with higher exponents, and you'll see when you expand this with a higher exponent, the higher the exponent, the longer this gets. But you can just do it. You can do it instantly. It won't take any longer than this took. Any questions? So let's talk about the meaning here of these, what we're doing. So we just found for an accumulation of 3x squared, the exact rate function was 6x. What does it mean that the rate function is 6x? Really important that we can all articulate this. So what does it mean that the exact rate of change of f is 6x? Anyone want to give it a shot? Somehow that somebody knew. Charles, what does it mean that our rate function is 6x for an accumulation function of 3x squared? Okay, and what's the output mean? What is the output? Okay, yeah. So f is accumulating at a rate, what rate? Or at a rate that's what? What can you say about the rate that f is accumulating at? Yeah, well. Yes, it's always the rate is going to be always 6 times whatever x value you're at, right? Okay, so suppose x is 2.1. How fast is this function f accumulating when x is 2.1? Excellent. 12.6. Now, what does that have to do with x and y? So if the rate, we know at x is 2.1, the rate is 12.6. Tell me how that relates to the quantities x and y. If the rate is 12.6, what does it have to do with x and y? Joe? At 2.1, the value of y is 12.6. Agree with that? So when you say the value of y, which value of y? What's the meaning of the y you're talking about? Okay, so the rate is 12.6 at 2.1. So what does the 12.6 mean? Okay, so it's like, yes, that's right. We can think of it as delta y over delta x. So what does it mean for how x and y are changing together, Connor?
Is it maybe 12.6? And if you were at that second, or at that point, where you multiply by the delta x out every dot little bit of accumulation?
Okay, yeah, we're getting, actually that's my next question. So you're bringing accumulation into it, and that's right. So, but what does it mean that the rate is 12.6 in terms of the quantities x and y?
It's like, y is accumulating 12.6 times faster than x when x is 2.1.
You said y is accumulating 12.6 times faster than x when x is 2.1. There were other hands. Who else had their hand up? Yeah, Will. Okay, so Will said at 2.1 for every 1 unit of change of x, you'll have 12.6 units of change in y. Joe? But so you're talking about the y value of this. So we want y to, if we're talking about y is going to be the accumulation. Y is accumulation, x is the same x, and then the rate. So that would be true if y were the rate. That would be true. Okay, but so both of what they said was right. So what did you say again? One more time? You don't remember.
I think I said y is
Accumulating.
12.6 times faster than x when
Yeah,
x is
that's excellent. She said y is accumulating. This is back, remember back constant rate of change, all the different ways we interpreted constant rate of change? If 12.6 is the constant rate of change, it's the relative size of changes in y and changes in x. So y is changing 12.6 times as fast as x. So what Will said, if x changed by 1, how much would y change? 12.6, because it's always changing 12.6 times as much as x. So if x went from 2.1 to 2.1001, how much would y change? How much would y change as x changed from 2.1 to 2.1001? What would our change in y be? Using the rate to find it. So you use the rate to find how much would y change. Nicole, any idea? Okay. Daniel. He wants 12.6 times the change in x. Nick, what do you think?
Wouldn't this be 6 times the change?
6 times the change in x. How much will y change when x changes from that to that? So we got 12.6 times the change in x and 6 times the change in x. Ben?
Would be 0.00126.
So you want 12.6 times the change in x.
I would say 0.0006.
6 times the change in x. What does this say again? How is x and y changing together? Y is changing how compared to x? Who said that? LJ, 12.6 times as fast. Y is changing 12.6 times as fast as x. So if x changes from 2.1 to 2.1001, how much will the quantity, how much accumulation will we get? Will it be 6 times this change? Or 12.6 times that change? Go.
Good question. If x changes, wouldn't that 12.6 also change?
Yeah, but it's such a small change that we can just assume. So that's like what we did all semester. Assume a constant rate for this very small change in x. Can we do that? Is that fair? Yeah. Well, you're right. One way, that's a good point. But we'll just assume a constant rate for that very small change in x. Connor.
The output of R is a rate, and then it has to be 2.1010.
Okay, so you're talking about what the final value of But no, that's not correct, because this is a change in x. All right, so this isn't a y value. So you're trying to kind of add a y onto an x there. See? Well,
Since you had a 12.6 change in y for every change in x.
okay.
Change in x is 8.0001. It'd be 0.0001 times.
That's it. So whoever, if you, and other people said that before, if y is changing 12.6 times as fast as x, then the change in, or the little bit of accumulation we'll get is 12.6 . Okay, again, y is always 12.6 as much as the change in x when x is 2.1. So if x was 3, we'd have something different because we'd have a different rate at x equals 3. Okay, this just goes back to delta y is k delta x, right? Changes in y are some constant multiple of changes in x. Okay, suppose we just had this rate function. How could we write an exact form accumulation for that rate? Everyone do this. Get a partner. What would, given that rate function, write an exact form accumulation based on that rate? Everyone should be able to do it. So you can write yours down, share it with the person next to you. Jack. Okay, somebody new. How's that? Integral? A, x. Okay, this has been offered up. Agree? Richard likes it? Likes it? Okay. So, so this is an exact form accumulation function for a rate of 6x, right? So, what function is that? What function is that? What is it? So, you're right, that's what we call it. But this particular one. So is this what is this? Is this a function of a or of x or of t? It's a function of x. What function of x is this accumulation function? Jacob, you're looking in the right place.
Rx.
No, Rx is 6x.
What were we asking?
Ben. Okay, which is? He wants 3x squared. Yeah? Yeah, because this rate was built from what? That accumulation. Okay, so if this is the rate of change of that accumulation, and then we take that rate and build the accumulation function from that rate, what accumulation function is it? It's the one we started with, right? I can get rid of all this. So this is the idea of accumulation, we built rate, and then we can use what we learned before. If we build accumulation, then those would be the same. Okay? So the accumulation that we built from this rate will have to be this function because we built that rate from that accumulation. Okay, and then just remember that sometimes we had a starting value of the quantity. So just mention this now. We'll talk about more of this later. But oftentimes we had a starting value from which we started accumulating. And so we have to just remember that there could be some number there. In this case, for this particular problem, it's 0. Okay, so we know that so this is the exact form of the accumulation function. No, I'm just not going to go to that. Okay, this is the exact form of the accumulation function, and so is this. And you remember about a week and a half ago we talked about if they're both the same thing, but they're in a different form. We want to have a name for that. So this is what we call the open form. It reflects the process. Okay, it reflects the process. What process does it reflect? And what's that, Ben? Yeah, what is that? So that notation reflects. What's that? Sum of all the little pieces, right? Sum of all the little bits that we're accumulating together. So that form reflects that, but it doesn't give us just a direct function, so we call it the open form. The direct function that just, well, all we have to do is plug in x and it tells us how much is accumulated up to that point, that's our closed form. So like I said, so when this process of adding up all the little bits produces a value of total accumulation, we get the same value as if using this function. Okay, there's something similar with our rate functions too. Okay, so here we set up this expression and then we found that it was 6x. Which one is open and which one is closed? Left is open or closed? Open reflects the process, doesn't give us just a function, r of x. So it reflects the process of building that rate step function and letting h get very small. And then that's the closed. Same thing. Okay, so when this process gives us a value of rate, we get the same rate if we use this. Okay, so we didn't make it. Don't have enough time for you to practice one. I wanted you to, say, do x to the 7th on graphing calculator. But if you were to do x to the 7th, some of you know from past calculus, if you were to work out that process, and we're still working out that process every time that I showed you using this expand and simplify, if you were to do it, you'd get 7x to the 6th. So how can you write then x to the 7th as an open form accumulation function? How could you write x to the 7th as an open form accumulation function? Jenica, you want to give it a try? How about, yeah, Kim. 7t to the 6 times dt. Make sense? Open form, using the rate. Closed form, which is the actual accumulation function x to the 7th. Okay, bring your laptops with graphing calculator. And get there right on time. You're going to need the whole time to work on that in-class sheet. Thanks.
Yeah, I scheduled one for midday.